Hi everyone. Through this class, we are going to study about rotational Raman spectra, vibrational Raman spectra, and rotational fine structure. First, we consider pure rotational Raman spectra of linear molecules. We know that rotational energy levels of a linear molecule is epsilon j equal to bj into j plus 1 minus dj square into j plus 1 whole square centimeter raised to minus 1, where this j is known as a rotational quantum number. Its values are 0, 1, 2, 3, etc. And b is the rotational constant and d the centrifugal distortion constant. And the value of B is h divided by 8 pi square IC. In Raman spectroscopy, the effect of the second term is negligibly small. So we can write this epsilon j in Raman spectroscopy as Bj into j plus 1 centimeter raised to minus 1. And here j is 0, 1, 2, 3, etc. And the transition between energy levels follows selection rule delta J equal to 0 or plus or minus 2. When delta J equal to 0, there is no change in molecular energy. Therefore, it represents the Rayleigh scattering. According to the convention, delta J is J of upper level minus J of lower level. And we know that J of upper level is greater than J of lower level. Therefore, always this delta J is positive. So we can ignore this delta J equal to minus 2 case. Now we have delta J equal to plus 2. The set of lines corresponding to this transition, that is known as S branch lines. And the energy difference during this S branch transition is epsilon J dash equal to J plus 2 minus epsilon of J dash equal to J. That is equal to, we know that energy is given by Bj into J plus 1. So, the level J when it is J plus 2, then it is B into J plus 2 into J plus 3 minus lower level energy, it is Bj into J plus 1. So, expanding this, it is equal to B into J square plus 5J plus 6 minus B into J square plus J, that is equal to B into this J square and J square term cancels. Now it is B into 5J minus Bj, that is B into 4J, then plus the 6. So we have B into 4J plus 6 where J equal to 0, 1, 2, 3, etc. If molecule gains energy during the collision with the photon, then we get a series of lines on lower frequency side. Such lines we call it as Stokes lines. So frequency of Stokes lines will be equal to nu s is equal to the incident frequency, that is frequency of the photon is nu 0, that minus the frequency change. Here this is in energy change in centimeter raised to minus 1, that is actually the frequency. So we can write it as minus B into 4J plus 6. Here our J value is 0, 1, 2, 3, etc. And during the collision with the photon, if the molecule gives energy to the photon, then the energy of the photon increases. Such lines we call it as anti-Stokes lines. And the frequency of anti-Stokes lines will be equal to nu as equal to nu 0 plus this change in frequency, that is B into 4J plus 6. And here also J equal to 0, 1, 2, 3, etc. Combining the equations for Stokes line and anti-Stokes line, the frequency is given by, that is the frequency of the scattered photon, that is nu bar equal to nu 0 bar plus or minus B into 4J plus 6 centimeter raised to minus 1. Here nu 0 bar is the frequency of the incident photon. Here the J is 0, 1, 2, 3, etc. And the rotational energy levels are like this. For J equal to 0, corresponding energy that is bj into j plus 1, that is equal to 0b. When j equal to 1, it is equal to 2b. J equal to 2, it is 6b. J equal to 3, energy is 12b. Next energy level is at 20b. Next level at 30b. Next one at 42b, and so on. And according to the selection rule, here the transition possible is for delta j equal to plus 2. That is from 0j level to 2 level transition possible. Then j equal to 1 to j equal to 3 possible. J equal to 2 to j equal to 4 possible. J equal to 3 to j equal to 5 possible. Again, from level j equal to 2 to 0 transition possible, and j equal to 3 level to j equal to 1 level possible, j equal to 4 to j equal to 2 possible. So, in this manner, from higher level to lower level transition is also possible for the molecule. And if there is no j change during a transition, that is delta j equal to 0. That corresponds to our Rayleigh line. So, if we take the spectrum of the scattered light, then we get the spectrum like this. At the center, we can see a strong line. That line is known as Rayleigh line. For this Rayleigh line, here the frequency is marked as nu zero bar. And during the collision, if the molecule jump from lower J level to upper J level, then we get a number of lines. That lines we call it as Stokes line. And if the molecule jump from higher J value to lower J value like this, then corresponding to each transition, we get a particular line in the spectrum at the higher frequency side, and that we call it as anti-Stokes lines. So this is the Raman spectra, and here we can see that here during this first Stokes line transition, that is from 0b to 6b transition, here the energy change is 6b. So from the Rayleigh line at a distance 6b, we get the first line. And on the right side at the same distance, we get another line. Here also energy change is 6b minus 0. So it is 6b. Then next line, here the energy changes. Here 12b minus this 2b, that is 10b. So from 10b distance from this Rayleigh line, we get this second Stokes line. So distance between first Stokes line and second Stokes line, it is 4b. Then at another 4b distance, we get the next line. Another 4b distance, we get another line. On right side, at the same 4b distance from the first line, we get the second line. Then at 4b distance, we get the third line, and so on. So, the difference between any two Raman line, here the energy change is 4b. And the separation between Rayleigh line and the first anti-Stokes or first Stokes line, that will be 6b. When we analyze the Raman spectrum, we can see that the intensity of Stokes line gradually increases, reaches a maximum with increase in J value, then decreases. For anti-Stokes line also, intensity of the lines are not constant. They gradually increases, reaches maximum, then decreases. And Stokes lines are more intense than anti-Stokes lines. This is because here the intensity of spectral lines, that is directly proportional to population of energy levels. And maximum population is for a particular J, which is equal to root of kT divided by 2hCb minus 1 by 2, where K is Boltzmann's constant, T absolute temperature, H Planck's constant, C velocity of light, and B the rotational constant. And the transition from lower J values and higher J values, the intensity will be small. Next, we consider why the rotational spectrum is not resolved for molecules with a larger moment of inertia. This is because we know that B equal to h divided by 8 pi square IC, where I is moment of inertia. When I is greater, we can see that B will be very small. That means gap between two adjacent spectral lines will be very, very small. So, we cannot see well-defined rotational spectrum for such a molecule with a larger moment of inertia. But for diatomic and light linear molecule, we get normally resolved spectrum. And if we can see these lines, Stokes lines and anti-Stokes lines, then we can calculate B value. And for homonuclear diatomic molecule, it do not give IR spectrum. But here we can see the well-defined rotational spectrum for this. This is because here there will be polarizability change during rotational motion. So we can study about such a molecule by taking Raman spectrum. For oxygen and carbon dioxide, energy levels with even J values are absent. That means J equal to 0 level, J equal to 2 level, J equal to 4 level, etc. are absent for this oxygen and carbon dioxide. So the first Raman line, that is at a distance of 10B from the central line. And the next line that is absent, so the next Raman line is for J equal to 3. So distance between J equal to 1 and J equal to 3, it is 8B. But in normal case, it is equal to 4B. And molecules made up of nuclei with non-zero spin and center of symmetry, they show alteration in intensities. Next, we consider vibrational Raman spectra. Molecule having n number of atoms, there will be 3n minus 6 normal modes of vibration. And if the molecule is linear, there will be 3n minus 5 normal modes of vibration. And all these modes of vibrations, they are anharmonic in nature. And the vibrational energy of an anharmonic oscillator is given by epsilon V equal to V plus half into nu bar E minus V plus half the whole square into Xc into nu bar E centimeter raised to minus 1, where V is known as vibrational quantum number. Its values are 0, 1, 2, 3, etc. And nu bar E is equilibrium vibrational or oscillational frequency. And Xc is known as anharmonicity constant. If the oscillator or vibrator is harmonic, then epsilon V is equal to V plus half into nu bar E. But here we consider it as anharmonic oscillator, so we need these two terms. And the selection rule for Raman transition is given by delta V equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. And V equal to 0 to V equal to 1 transition, that is known as fundamental transition. And energy change during this fundamental vibrational transition is equal to epsilon 1 minus epsilon 0 equal to, here we put this V as 1. So it is 1 plus 1 by 2, that is 3 by 2 into nu bar E minus 1 plus 1 by 2 whole square into Xc into nu bar E, that is 9 by 4 Xc into nu bar E, that minus energy of the lower level with V equal to 0. So it is 0 plus 1 by 2 into nu bar E, that is 1 by 2 nu bar E minus square of 1 by 2, that is 1 by 4 Xc into nu bar E. That is equal to nu bar E into 1 minus 2Xc. V equal to 0 to V equal to 2, 3, 4, etc. transitions, they are known as overtones. V equal to 0 to V equal to 2 transition is known as first overtone. V equal to 0 to V equal to 3 level transition is known as second overtone and so on. Energy change during first overtone transition is epsilon 2 minus epsilon 0 equal to 5 by 2 nu bar E minus 25 by 4 Xc into nu bar E minus 1 by 2 nu bar E minus 1 by 4 Xc into nu bar E. That is equal to 2 into nu bar E into 1 minus 3Xc. V equal to 1 level to V equal to 2 level transition is known as hot bands. V equal to 1 level is populated only at very high temperature. So, the transition from these levels are known as hot bands. And energy change during this hot band transition is epsilon 2 minus epsilon 1 is 5 by 2 nu bar E minus 25 by 4 Xc into nu bar E minus 3 by 2 nu bar E minus 9 by 4 Xc into nu bar E, that is equal to nu bar E into 1 minus 4 Xc. Population in 1, 2, 3, etc. levels are negligible. Since Raman scattering is weak, overtones and hot bands are rare in Raman spectra. So we want to consider only the fundamental transition. So corresponding to active mode of vibration, the Raman frequency is given by nu bar equal to nu 0 bar plus or minus nu bar E into 1 minus 2Xc. And in this expression, the plus corresponding to anti-Stokes Raman line and minus corresponding to Stokes Raman line. Therefore, Stokes Raman line frequency is given by nu bar S equal to nu 0 bar minus nu bar E into 1 minus 2Xc, and anti-Stokes Raman line is nu bar AS equal to nu 0 bar plus nu bar E into 1 minus 2Xc. Next we consider rotational fine structure. Rotational fine structure is resolved only for light diatomic molecules. Here we consider the vibrating rotator, and the energy for a vibrating rotator is represented as epsilon Vj, that is equal to sum of vibrational energy and rotational energy. And we know that vibrational energy for an anharmonic oscillator is V plus half into nu bar E minus V plus half the whole square into Xc into nu bar E, and that of rotator is Bj into J plus 1. Here V is known as vibrational quantum number and J the rotational quantum number. V and J can take value 0, 1, 2, 3, etc. And for rotational transition, the selection rule is delta J equal to 0 plus or minus 2. When delta J equal to 0, that branch of lines it is Q. Delta J equal to plus 2, it is S branch. Delta J equal to minus 2, it is O branch. In a particular vibrational energy level, there are number of rotational energy levels. So, if the lower vibrational level is marked as V double dash, then in that V double dash level, there will be number of rotational levels with J value 0, 1, 2, 3, etc. The upper vibrational energy level, if it is V dash, in that V dash level, there will be number of rotational energy levels with J equal to 0, 1, 2, 3, etc. So from lower vibrational level to upper vibrational level transition, the delta J can change by minus 2 also. So here there will be O branch lines along with S branch and Q branch. For Q branch transition, delta J is taken as 0. That means there is no change in rotational energy. So we want to take only change in vibrational energy. So for Q branch line transition, nu bar Q equal to nu 0 minus nu bar E into 1 minus 2Xc. Because when delta J equal to 0, V equal to 0 to V equal to 1 level transition, energy change in vibrational level is equal to nu bar E into 1 minus 2xe. And for S branch line transition, here V value changes from 0 to 1 and delta J also changes by plus 2. So, total energy change delta epsilon of V and J, that is equal to this energy change nu bar into 1 minus 2xe plus change in rotational energy, that is equal to B into J plus 2 into J plus 3 minus Bj into J plus 1. So, here the total energy change equal to nu bar E into 1 minus 2xe plus B into 4j plus 6 centimeter raised to minus 1, where j equal to 0, 1, 2, 3. Therefore, the frequency of S branch Stokes line is nu bar S is equal to original frequency nu 0 bar minus change in frequency. So it is equal to minus nu bar E into 1 minus 2xe minus B into 4j plus 6 centimeter raised to minus 1, where j equal to 0, 1, 2, 3, etc. For O branch, here the transition is from V equal to 0 level to V equal to 1 level and delta J changes by minus 2. So change in energy delta epsilon Vj equal to nu bar E into 1 minus 2xe plus B into J double dash minus 2 into J double dash minus 1 minus B J double dash into J double dash plus 1. So here it is equal to nu bar E into 1 minus 2xe minus B into 4j double dash minus 2. So for getting delta J equal to minus 2, the first transition is from J equal to 2 to upper J equal to 0 value. Next transition is from lower J equal to 3 to upper J equal to 1 level. So here this J double dash in this case is 2, 3, 4, etc. And the frequency corresponding to O branch Stokes line is nu bar O equal to nu 0 bar minus change in frequency. So it is minus nu bar E into 1 minus 2xe. Here already there is 1 minus, so minus minus become plus. So plus B into 4j plus 6 centimeter raised to minus 1. For this j we can take it as 2, 3, 4, etc. The rotational fine structure of diatomic molecule is shown here. Here this line is the Rayleigh line and this is the Stokes vibrational transition line, that is at a distance of nu bar E into 1 minus 2xe. On both sides of this first Stokes line we can see number of lines. They are due to the rotational transition. This is due to the S branch lines and this is due to the O branch lines. And the weaker anti-Stokes line occur at the same distance nu bar E into 1 minus 2xe on the other side, that is on the higher frequency side, that is not shown here.